In a moment, we're going to read from O'Connor Sloane's book. But first, it is useful to establish a few concepts using the language of James Jeans's The Mathematical Theory of Electricity and Magnetism, and then connect those older geometrical ideas with the modern calculus that Sloane is performing. The image begins at the upper left with potential. Imagine a positive electric charge surrounded by a series of concentric surfaces. Each surface represents a particular value of electric potential, an electrical level. Potential itself is a scalar. At every point in space, we simply assign a number. The concentric circles in the picture are therefore like contour lines on a geographical map. Each one says the potential has this value here. Beside that picture, we see the first important mathematical operation, the gradient. If we know the potential at all these places, we can ask how rapidly it changes as we move through space. The gradient measures that spatial slope. The electric intensity points in the direction in which potential falls most steeply. Thus, the arrows radiating away from the positive charge in the next picture are the lines of electric force. In Jeans's geometrical language, these lines may be grouped together into tubes of force. Notice something important about the two pictures. The lines of force cross the equipotential surfaces at right angles. Moving along an equipotential produces no change of potential. Moving along a line of force produces the greatest change of potential per unit distance. The closer together the equipotential surfaces become, the more rapidly the potential is changing, and therefore the stronger the electric intensity. So the first relationship shown in the image can be spoken very simply. Open quote. Start with electrical level. Examine how steeply that level falls through space. The steepest fall gives the direction of the lines of force, and the amount of fall per unit distance gives their intensity. Close quote. In modern calculus, this is the negative gradient of potential. The upper right picture then performs the journey in reverse. Here we are no longer starting with potential. We imagine that we already know the electric intensity. The picture shows a tube of force running from point A to point B. The electric intensity lies lengthwise along the tube. Now imagine traveling along it. Over every tiny piece of the journey, there is a certain electric intensity acting through a certain tiny distance. We accumulate all those tiny contributions from A to B. That accumulation is an integral along the line, and it gives the potential difference between A and B. This is particularly close to what Sloane is about to do. He knows the force at different distances and asks how much work is accumulated in moving through those distances. From that accumulated work, he obtains potential. So the two upper pictures are inverses of one another. Open quote. Potential differentiated through space gives intensity. Intensity integrated along space gives potential difference. Close quote. In Jeans's tube language, we can think of this as the lengthwise mathematics of a tube of force. But the lower left picture asks an entirely different question. Instead of traveling along a tube, imagine placing a tiny box around a point in the field. Now ask, open quote, are more tubes leaving this little region than entering it? Close quote. If more leave than enter, the region behaves as a source. The first little cube in the image illustrates this. Arrows emerge outward. Electrically, that corresponds to positive charge. If more tubes enter than leave, we have a sink. That corresponds to negative charge. And if exactly as much tube strength leaves as enters, there is no source or sink inside that little region. This is divergence. So divergence is not asking about the lengthwise fall of potential. It is asking about the local bookkeeping of the tubes themselves. Jeans's language is exceptionally helpful here. Open quote, do tubes originate here? Do they terminate here? Or do they merely pass through? Close quote. Modern calculus compresses that geometrical question into the divergence of the electric field, and Gauss's law tells us that this divergence is related to charge density. The center-right part of the image then brings these ideas together. We begin with potential, the electrical level. Take its gradient and we obtain electric intensity with magnitude and direction. Take the divergence of that electric intensity and we discover charge density, the local source or termination of the tubes. But we can also travel backwards from electric intensity to potential by integrating the intensity along a path. So there is a little conceptual circuit. Open quote, potential tells us the level, gradient tells us the slope and therefore the field. Divergence examines whether that field has a source. Integration along the field reconstructs differences of potential. Close quote. Finally, at the bottom of the image, these operations combine into something that can otherwise sound rather mysterious, the Laplacian. The Laplacian of potential simply means, open quote, first find the spatial slope of potential, the gradient, and then ask whether the field produced by that slope has a local source or sink, the divergence. Close quote. So the Laplacian is the divergence of the gradient. This is where Jeans's Poisson and Laplace equations enter naturally. Where there is charge, the curvature of the potential is related to that charge. That is Poisson's equation. Where there is no charge, there can be electric intensity and lines of force passing through, but there can be no local creation or destruction of the tubes. There, the potential obeys Laplace's equation. And this gives us the background for Sloane. Sloane is about to approach these ideas in a much more concrete way. Rather than beginning with the compact machinery of vector calculus, he starts with forces, distances, components, and infinitesimal pieces, and adds them together. As we read him, we can therefore keep Jeans's picture in mind. Potential as electrical level, intensity as the directed action down that level, lines and tubes as the geometry of the field, integration as accumulation lengthwise along those tubes, and divergence as the question of where those tubes begin or end. Force exerted by an infinite plane on a point at a finite distance. Let AB represent the section of a plane, and let M represent a mass which is attracted by that plane. Let sigma represent the attraction belonging to one unit area of the plane. Then a unit area of the plane, when situated at unit distance, attracts the mass with an attraction represented by M multiplied by sigma. At some general distance, r, the inverse square law applies. The force is therefore m multiplied by sigma divided by r squared. Sloane calls this force F. Now, this is not yet the force which attracts the mass directly toward the plane. A particular small portion of the plane will generally lie off to one side of the mass. The force due to that portion acts along the sloping line joining that portion of the plane to the mass. What we require is only the component of this force which acts perpendicular to the plane. Calling the angle between the perpendicular distance, p, and the sloping distance, r, alpha, and calling the perpendicular force f prime, the perpendicular force is the original force multiplied by cosine alpha. Since the original force is m sigma divided by r squared, the perpendicular force is m sigma divided by r squared multiplied by cosine alpha. But from the geometry of the triangle, cosine alpha equals the perpendicular distance p divided by the sloping distance r. Consequently, the perpendicular force becomes m times sigma times p divided by r cubed, and very familiar in modern vector calculus. Sloane has a force possessing a magnitude and a direction, but he wants only the part acting in one selected direction, the direction normal to the plane. Today we would describe this as taking the normal component of the force vector. The dot product is the natural modern operation for doing precisely this. So when Sloane multiplies by cosine alpha, mentally read, project the force onto the normal direction. This is also the same geometrical operation that appears when we calculate electric flux through a surface. Only the part of the field passing normally through the surface counts fully. Now Sloane has to add the effects of every portion of an infinite plane. Instead of dividing the plane into arbitrary little pieces, he uses the symmetry of the problem. Imagine the point on the plane immediately underneath the mass. Around this point, draw a circle of radius h. Now draw a second circle, concentric with the first, whose radius is h plus the infinitesimal amount, dh. The very narrow strip lying between those two circles is an annulus. Its area is 2 pi times h multiplied by dh. Every point around this annulus is at the same sloping distance r from the mass. That is why this particular division of the plane is so useful. Instead of dealing separately with every little piece around the circle, Sloane can treat the entire circular annulus together. Now the perpendicular distance p remains fixed. The radius h along the plane and the sloping distance r are related by Pythagoras. R squared equals h squared plus p squared. Sloane differentiates this relation. Since p is constant, its differential contributes nothing. The differential relation therefore says 2r times dr equals 2h times dh. Dividing both sides by 2 gives r dr equals h dh. Sloane can therefore replace h dh in the expression for the annular area by r dr. The area of the annulus, originally 2 pi h dh, can consequently be written 2 r dr. Comment: there are act hiding in this short step. First, Sloane differentiates a geometrical constraint. He has a relationship between two changing distances, and differentiation tells him how an infinitesimal change in one corresponds to an infinitesimal change in the other. Second, he performs what we would now call a change of variable. He began describing the annuli using their radius h along the plane, but his force law is naturally expressed using the sloping distance r, so he converts the area element from something involving h into something involving r. This is exactly the sort of manipulation that later becomes systematic in multiple integration. Now the annulus is an infinitesimally small portion of the whole plane. Sloane therefore regards its area as a differential area, which he calls ds. Thus ds equals 2 pi r dr. We already know the perpendicular force produced per unit area. It was m sigma p divided by r cubed. To obtain the perpendicular force produced by the entire infinitesimal annulus, multiply the force per unit area by the infinitesimal area. So we multiply m sigma p divided by r cubed by 2 pi r dr. 1 power of r cancels. The infinitesimal contribution to the perpendicular force therefore becomes 2 pi times m times sigma times p times dr divided by r squared. Now Sloane integrates. That means that he adds the contributions from all the concentric infinitesimal annuli, which together constitute the infinite plane. The nearest part of the plane occurs directly underneath the mass. There h is 0, and consequently the sloping distance r is simply p. At the opposite extreme, the annuli extend outward without limit, and r approaches infinity. So the total perpendicular force is 2 pi m sigma p multiplied by the integral from r equals p to r equals infinity of dr divided by r squared. The integral of 1 divided by r squared produces minus 1 divided by r. Evaluating between the limits gives 1 divided by p minus 1 divided by infinity. 1 divided by infinity tends to 0. So the remaining 1 divided by p cancels the p, which was sitting outside the integral. The final result is therefore 2 pi times m times sigma, and this result contains no p, the attraction of t independent of the distance from the plane. Comment: this is exactly where Jeans helps Sloane has reached this result by what we might call the microscopic summation route. Take every little piece of charged plane, find its individual inverse square action, resolve that action into the normal direction. Then add all those contributions by integration. Jeans gives us another way of thinking about precisely the same result. Think in terms of tubes of force. For a point charge, the tubes spread outward in every direction. As you go farther away, the same collection of tubes has to occupy a larger spherical area. Their concentration therefore decreases. That produces the inverse square weakening. For an infinite plane, however, the geometry is completely different. The lines leave the plane normally and remain parallel. The tubes do not spread out as they travel away from the plane. Their cross-sectional area remains constant. Therefore, their concentration does not diminish, and consequently, the electric intensity remains constant. So Sloane's integral has laboriously demonstrated something which Jeans's tube geometry makes almost visible. There is also a nice connection with divergence. Away from the charged plane, there is no charge. So locally, there is no source of electric tubes. The divergence is zero. At the charged plane itself, however, the plane acts as the source from which the electric field emerges. Thus, the discontinuity at the plane is where the charge enters the field description. Now, absolute potential. Sloane now changes the problem. Let E represent a quantity of electricity concentrated at a point O. This point is therefore a center, or locus, of attracting or repelling force. Now imagine an indefinitely small test body being moved from a position at distance r from O to another position at distance r prime from O. Whatever path is followed in making this journey, Sloane says that the net radial displacement is represented by the difference between the two distances. The force acting upon the test body at distance r is E divided by r squared. Now suppose the body is moved through an infinitesimally small distance, dr. The infinitesimal work or energy associated with that movement is the force multiplied by the infinitesimal displacement. Thus the infinitesimal energy is E divided by r squared multiplied by dr. If the body is moved through a finite distance, Sloane obtains the total energy by integrating these infinitesimal pieces of work. So he takes the integral of E divided by r squared times dr between the initial and final distances. Performing the integration gives E multiplied by the quantity 1 divided by the first distance minus 1 divided by the second distance. This is the energy involved in moving unit quantity from one position to the other. Absolute potential at the point whose distance is r. To obtain it, he takes the other reference point to infinity. So imagine bringing unit charge from infinitely far away to the point at distance r. The potential becomes E multiplied by 1 divided by r minus 1 divided by infinity. Again, 1 divided by infinity tends to 0. Therefore, the absolute potential is simply E divided by r. Comment. Now connect this directly to what we've been discussing. This is the relationship between potenti is traveling from intensity to potential. He begins with the local force, E divided by r squared. That is the local electric intensity. He then asks, open quote, if I travel lengthwise through this field, how much of this local action accumulates over the entire journey? Close quote. Integration answers that question. So intensity integrated lengthwise gives potential difference. And if we reverse the operation, the spatial rate of change of potential gives intensity. That reverse operation is the gradient. So if Jeans gives us potential everywhere in space, we can ask how rapidly the potential falls as we move. The steepest fall determines the direction of the electric line of force. The magnitude of that fall per unit distance determines the electric intensity. If instead Jeans gives us the electric intensity and we travel along the tube, accumulating intensity times distance, we reconstruct the potential difference. That is why your earlier description of this as the lengthwise property of the tubes is useful. Potential difference concerns what accumulates as we travel along the tube. Divergence asks something different, whether the tube structure is being created or terminated locally, and therefore we now have three closely related operations. Integration along a line of force, intensity becomes potential difference. Gradient of potential, potential becomes intensity and gives the lengthwise direction of the lines. Divergence of intensity, the tube structure tells us where charge, the source or sink, is located. Put gradient and divergence together and we arrive at the Laplacian of potential. That is the modern vector calculus structure sitting underneath Sloane's much more concrete calculus demonstrations.